Swayam Prabha. Digital India. Educated India.
Welcome to Module E, Lecture 7. This is the first lecture in this week. Today, we shall discuss about pre-timed signal design. In Lecture 6, I mentioned to you about various performance measures, for example, delay, volume to capacity ratio, queuing, and then discussed in details about the delay as performance measures. I mentioned to you about stop delay, approach delay, travel time delay, also discussed about various delay scenarios, theoretical modeling of delay, and then why the inconsistencies in random and overflow delay models are there and how to overcome that using a different model. Now, we shall continue our discussion about what I said, pre-timed signal design. The first and one of the very popular and well known method is the Webster method. So, we shall start our discussion with the Webster method. As per Webster method, the cycle length corresponding to minimum intersection delay may be obtained using the formula as shown in the slide. Here we are using L as the total lost time per cycle. Y I is the maximum value of the ratios of approach flows to saturation flows for all lane groups using phase I, and like that every phase maximum value of the ratio that we add up for all the phases and then 1 minus sum of that, or sum of y I equal to 1 to phi, phi is the number of phases. Now, the lost time for phase I, as we have discussed earlier, is green time, whatever is given overall green, plus yellow or amber minus the effective green time. So, the actual green time, amber and effective green time, that way we can calculate the lost time per phase. Now, then what is the total lost time? Total lost time is sum over L I for sum over all the phases I plus all red time. Here in the above equation, L I equal to G I plus Y I minus small g I effective green time. Here we only considered Y I as the YOLO time. So, the all red is not included here in this phase wise lost time calculation. So, when we are calculating the total lost time, we are calculating the lost time plus the all red time considering all the phases. So, here is the total all red time during the cycle. So, all the phases are considered together. Now, then the total effective green time available per cycle will be how much? Cycle time minus total lost time, C minus L. Then what we are saying, effective green time, this G total, how we are distributing? We are distributing in proportion of basically Y. So, Y I by sum over Y I, right. So, how much share one particular phase I will get, that is Y I divided by sum over Y I. That way the effective green time is distributed to different phases. Now, then what will be the actual green time for each phase? Actual green time will be effective green time plus loss time for that phase minus the YOLO time or amber time for that phase. So, that way we can get the actual green phase. Let us take an example to understand it even in a better way. Determine a suitable signal timing for the given intersection using the 4 phase system, and for each phase y equal to 3 seconds, AR, this AR is small AR, that means each phase wise AR is 1 second and total loss time is 3.57 and peak hour factor is 0.95. Now, this is a 4 phase system, that is what is assumed here. You know there are 4 approaches to this intersection, and each phase we are actually clearing traffic approaching from one approach. So, first maybe eastbound, then westbound, not southbound, northbound. And you can see here from each approach there are 3 lanes. One in an exclusive right turn lane, then the leftmost lane is straight and left shared, middle lane is for the through traffic. So, the saturation flow values are also given from each approach. Right turn say 1615, through and left 3700, through and left mean it is both the lanes together, where the left lane is through and left and the middle one is only through. So, together the saturation flow is 3700. Exactly in the similar manner for different phases, the westbound, southbound and northbound, the saturation flow values for the right turn and through plus left together that are given. So, with this input we need to design a suitable signal timing. What we are doing here? Look at this table, phase wise we take A, B, C, D 4 phases. Lane group we consider here eastbound first, then westbound in phase 2 or phase B, southbound in phase C and northbound in phase D. In each phase 2 lane groups we are considering, one is for exclusive right turn, the other through and left together, the leftmost lane and the middle lane together. Now, if you take that, then hourly volumes per lane as it is given in the previous page, the same values are taken. For example, if you take eastbound right turn, it is 128 vehicles. Eastbound right turn you can say it is 128. Similarly, the straight is 321, straight and left combined or shared lane is also 321. So, same way we take the values 321. Here in phase C through and left the values are not same, like in this case 321 and 321 both were 321, but for eastbound the values are different. 75 is straight and 109 straight and left. So, we add them together and then say this is the not volume per lane truly, but these are the volumes in 2 lanes. I should not use the plus sign here. Then what we are trying to get here in the next column is equivalent hourly volume. So, what is the difference between the hourly volume and equivalent hourly volume? In equivalent hourly volume, we have considered the peak hour factor. That means hourly volumes per lane is calculated considering the peak hour factor. That means considering the peak 15-minute hourly flow rate rather than the hourly volume, peak 15-minute hourly flow rate. So, you can see the peak hour factor is 0.95. So, 128 by 0.95 you will get 135. Similarly, for each case we calculate the values. Again here also not 79 plus 115 in true sense, but what we are trying to indicate that you have one lane where the volume is hourly volume is 75, and when you take the equivalent hourly volume considering the peak hour factor it is 79. Similarly, for another movement it is 109 and the equivalent value is 115. Of course, eventually these are to be added together when we will consider the hourly equivalent hourly volume, not per lane, but total. So, here since for the first case phase A eastbound there is only one lane. So, the 135 will remain 135, but through and left in each case 321, the left and straight shared lane is 321, straight is also 321, and the equivalent hourly volumes considering the peak hour factor is 338. So, the total will be 338 plus 338 equal to 676. Similarly, here it is one lane. So, 234 remains 234, 488 again it becomes double because one is through and left shared with 488 equivalent hourly volume per lane in one lane, and then another case straight also is 488 equivalent hourly volume. So, together approach wise it is 976, 26 remain, and in this case for phase 3 southbound the two values we have to add together. So, 79 plus 115 is 194. Why we are adding them together? Because the left and through combined saturation flow are considering both the lanes. One is a shared lane through and left, the other is only a through lane. So, together the saturation values are given. So, hourly equivalent volumes, total volumes also we are taking the total volume. Now, once the saturation flow is known from the previous table, inputs given as inputs. So, we can calculate then Q I j divided by S j, each flow divided by the corresponding saturation flow. Now, in phase A, what we said here? If we go back, we said what is Y I? Maximum value of the ratios or of approach flows to saturation flows, maximum value of the ratios of approach flows to corresponding saturation flows. So, if you come here, there are two values here, one is 0.084, another is 0.183. What is maximum of these two? 0.183. Similarly, 0.145, 0.264. What is the maximum of this? 0.264. Similarly, here it is 0.052, and for phase D the Y I is 0.230. So, then what is the sum over Y I? Add all these four values and that becomes 0.729. Fine. Now, what is the total lost time? Lost time is lost time per phase plus the all-read time for the whole cycle. So, we know there are 4 phases, each phase the lost time is 3.5 seconds given as input, total lost time is 3.5 seconds per phase. So, total lost time is 3.5 plus 4 into 1 second. Here it is also the all rate small AR. So, it is phase wise. So, 4 phases together is 4 seconds. So, total is 18 second lost time. So, now with all these values known value of L, known value of sum of yi, we can get the optimum cycle length, which we are getting here as 118 seconds. So, what will be then, if this is the cycle length, then what is the total effective green time? Is the cycle time minus total lost time. Cycle time is 118 and total lost time is 18. So, the effective green time is 100 seconds. Now, these 100 seconds are to be distributed to 4 phases. In what ratio? yi by sum over yi. So, first phase A, how much share we will get? Phase A will get 0.183 divided by 0.729. Phase B will get 0.264 by 0.729 and so on. So, what we have done here, 100 seconds multiplied by effective green time for A is 0.183 by 0.729. So, 25.1 second. Similarly, for phase B, the effective green time is 36.2 second, phase C 7.1 second, phase D 31.6 second. Now, what will be then the actual green time? Actual green time for each phase, say for phase A will be effective green time for phase A plus the lost time, total lost time is 3.5 seconds, right, per phase. So, that will be there. So, minus 3 is the yi. So, you take out that, it becomes 5.6 second. Similarly, you calculate the total or actual green time for phase B, phase C and phase D. We can also do a check whether we have really distributed it correctly. We can do that check, because if you add up GA plus GB plus GC plus GD, it becomes 118, which is exactly equal to whatever you got as the total effective green time. Okay. So, total value that we can see, not total effective green time, sorry. So, the total cycle length, because we are getting here the total green time. So, total green time together, right, GA plus GC plus GB plus GD all together, plus you can get all the YOLO time, add them. So, 26 5.6, 36.7, 7.6 and 32.1 plus all the corresponding YOLO time and all read time. So, 4 seconds, 4 seconds, 4 seconds, 4 seconds. So, if you get that, what you will get? You will get the cycle time. Now, going to the next part, critical length and time budget concept. Now, two components we are talking. We are talking about critical length and also we are telling about time budget. Critical length is used to identify specific lane movements that will control the timings of a given signal phase. In one signal phase, multiple movements are happening. So, we want to find out the critical lane that will control the timings of a given signal phase. So, that means, if the critical lane is served, then obviously all other lanes also will be served. And time budget is actually used for the allocation of budgeted time to various vehicular and pedestrian movements at an intersection through signal controller. What is the time budget? Because we have total time available per hour is 1 hour or 3600 seconds in an hour. So, I have all what I have is available is 3600 seconds. Now, how this 3600 seconds we shall utilize for different things. Now, what is the total lost time per cycle if there are a number of phases in a cycle and if small t L is the total loss time per phase. So, there are n phases in one cycle. So, per cycle what is the loss time? N into T L, easy. Then what is the total loss time in an hour? That is loss time per cycle multiplied by number of cycle in 1 hour. So, you have 3600 seconds and capital C is my cycle length. So, how many cycles are there? 3600 by C. Each cycle what is the loss time is L. So, then what is the total loss time per hour? LH equal to L into 3600 by C. Then total effective green time in an hour, how much is available then total green time? I have 3600 minus total loss time per hour is LH. So, it is 3600 minus LH. Now, this is the effective green time. So, how many vehicles I can process? It is simply at the rate of H saturation headway. So, this whole Tg time may be used at a rate of 1 vehicle per H second, where H is the saturation headway. That much discharge I can do. I can handle, I can process that many vehicles, correct. Now, signal timings and design must accommodate the total demand flows in critical lengths. That is what is my basis. In every phase, I should be able to handle the critical lane. So, critical lane is the lane with most intense traffic demand. Carefully observe it. I am saying most intense traffic demand, not necessarily the lane with the highest volume. So, on what basis we are identifying the critical lane? It is based on the highest volume to saturation flow. Why this? Because if all lanes are equal, suppose all are single lane, then I can compare only based on the traffic volume. Then highest volume is the critical one, the one which is having the highest volume will be the critical one. But suppose one of them is actually having 2 lane, then per lane traffic will be total by 2, and if it is so, I cannot simply compare the volume, but it is volume by saturation flow, right. So, highest volume to saturation flow, that will be the critical lane. I shall also take an example to explain you further. Now, whatever is this green time available, effective green time Tg at the rate of h seconds per vehicle. So, how many vehicle I can handle? Vc, the critical vehicle volume or critical lane volume, Tg by h. Now, if you take, then Vc equal to Tg by h. What is Tg? Tg is 3600 minus LH. So, 3600 minus something. What is LH? LH is L into 3600 by C. So, L into 3600 by C, and what is L? L is N into T L. So, with all the substitution, how much you get? You get that Vc equal to actually 3600 into N into T L within bracket 3600 by C, the whole thing divided by H. That is the critical volume that can be handled. So, if this is the critical volume, then what is the minimum cycle length? Just from this equation only we can get. We can get here then what is C in terms of V c, N, T L and H. That is what exactly I have done it. So, that is the minimum cycle length required, N as a function of N, T L, critical volume and H. Now, this gives you the minimum cycle length, but when we are proposing, we will propose something what we will call as design cycle length. Now, minimum cycle length to design cycle length, two more additional considerations. First, we now bring here peak hour factor. Why we are bringing the peak hour factor? Because so far you have considered hourly volume in the calculation, but what we need to do? We need to consider peak 15-minute hourly flow rate rather than the hourly volume. So, peak hour factor is introduced here to estimate the flow rate in the worst 15-minute period. Worst in this sense is the maximum flow rate of the peak hour. So, that is why the peak hour factor is coming. This is one change from the C minimum to C design. The other consideration here you can see I have written here something called V by C ratio. What is the V? V by C ratio is the desired volume to capacity ratio. Why this one? Because if you consider, just do not consider this thing, then how we shall consider the normal stochastic variation in demand? Most signals would be timed to have 80% to 95% of the available capacity, not 100% of capacity. So, we do not use V by C as 1, which is there somewhere other in the C minimum calculation. Why we do not use it? Because there will be normal stochastic variation in demand. So, if we consider it only 1, V by C as 1, then how we will handle this stochastic variation? Because in that case you are taking V by C as 1, but due to stochastic variation there will be individual cycle failure and also multiple cycle failures or several cycle failures, such failure may happen during the peak periods. So, considering normal stochastic variation in demand, most signals would be actually timed to have 80 to 95% of the available capacity. That means, it will be designed considering V by C as 0.8 to 0.95, so that the normal stochastic variation in demand in cycle to cycle can be handled properly to avoid failure of individual cycles or peak periods, right. Now, let us take an example. Signal at a location has two phases with a cycle length of 60 seconds, a very simple one, a two phase signal, no other movements are allowed. So, this straight and this straight. So, one is the eastbound, another is the northbound, and suppose the cycle length is 60 seconds. Somebody has proposed that okay, let us use cycle length of 60 seconds. Now, if the total loss time is 4 seconds per phase, saturation headway is 2.3 seconds per vehicle and peak hour factor is 0.95 and target V by C is 0.9. I said there 80 to 95%. So, here it is considering say 0.9. Then what we want? We want two things here. First, determine if the given cycle length will satisfy the requirement of minimum required cycle length to accommodate critical lane volumes. So, we want to see whether it is satisfying the requirement of minimum required cycle length, C minimum, whether it is satisfying or not. Second, if not, find the appropriate number of lanes required for each lane group and then what is the desirable cycle length. So, what we do first? For the cycle length of 60 second, the critical length flows that can be accommodated, we can calculate it V c. How we are calculating? Let us go back again to remind you this one, right, T g by H essentially, right. So, here based on that we are calculating the value of V c, how much critical volume that the intersection will be able to handle given the cycle length, giving the lost time, number of phase and saturation headway. So, that we are calculating, and in this calculation since it is C minimum, we are not using the peak hour factor and target V by C value, because that those two will come when we will talk about part B, that is the desirable cycle length or design cycle length. So, here you can see V critical is 1357. So, that means with that cycle length, if that is the minimum we considered, right, then we can maximum handle 1357 vehicle per hour, whereas our present volumes are how much? It was given here, also reproduced here, 1800 plus 1200, 3000 vehicle per hour, whereas with the given cycle length, even if we consider the minimum required, that as the minimum required cycle length, then we can maximum handle 1357 vehicles. So, it will not work, right. So, the critical northbound volume and critical eastbound volume together is 3000 vehicles, higher than V c. So, it cannot be accommodated. The first question is answered. Then second, what we are trying to do? We are trying to see, let us see, then if my critical volume is 3000 vehicle per hour, then what will be my design or desirable cycle length? You calculate it, you get a value negative minus 6.44. What this negative value is indicating? That no cycle length, this cycle length, you cannot get a cycle length which can accommodate this critical volume of 3000 vehicle per hour at this location with this many number of lanes and with this all other parameters, saturation headway 2.3 second, total loss time 4 second per phase, peak hour factor 0.95, target V by C as 0.9. With all these, it cannot, you cannot get a cycle length which will be able to accommodate this critical volume. So, now what we do? Okay, let us go step by step. We know that the maximum volume here it was eastbound, which is 1800 maximum. So, we say instead of one lane, should we have two lane there? Let us try with that. So, if we give two lane, then each lane will have 900 volume. Then what will be the critical volume? 2100 vehicle per hour. Okay, let us try to calculate again the C design or desirable cycle length can we get? What we get? Still it is negative, indicating still it is not working. Fine. Next, we thought that okay, let us try, we made there as 2 lane, the other movement also let us have 2 lane. So, the 1200 also will get distributed to 600, 600. Now, there will be 2 lane. So, now with 2 northbound lane and 2 eastbound lane, what will be my critical volume? Critical volume will be 1500 vehicle per hour. With that again calculate C design, still it is minus 66.2, right. So, the desirable cycle length still we are not getting, it is still showing even if with two lanes on the northbound, two lane in the eastbound, with all other things and the given traffic volume, we cannot get a signal cycle, designed signal cycle or desirable cycle length, which can handle this traffic at this intersection. Go for further trial. Here we consider two lane northbound and three lane eastbound. Then what is happening? 1800 divided by 3 lane 600, northbound 1200 divided into 2 lane 600 in each. So, now my critical volume becomes 1200 vehicle per hour. Now, let us see what happens. Now, when we calculate C design or desirable, we get the cycle length as 77.4 positive value and we are able to get it. So, that means it will work. I also wanted to calculate here the C minimum, and with this configuration, that means 2 northbound lane and 3 eastbound lane, your total minimum cycle length will become 34.3. You can clearly see that the desirable cycle length, when you consider the peak hour factor and V by C ratio lower than 1, then your actually desirable cycle length will be much higher. So, while the minimum cycle length requirement is 34.3, the desirable cycle length is 77.4. So, altogether what it shows, C design is greater than C minimum, because of the equation C design takes it into account both the peak hour factor and target V by C ratio. And how or what is going to be our recommendation from this one? That you widen the northbound movement, widen it to 2 lane and eastbound movement to 3 lane, accommodate the eastbound movement in 3 lane, accommodate northbound movement in 2 lane, have a desirable cycle length of 77.4 seconds or 78 seconds. That is what is our recommendation. We see a few important observations here. Critical relationship between the number of lanes and the cycle length is illustrated, because if you are increasing the number of lanes in the approach, then your traffic is actually demand is getting distributed. So, the critical volume that the signal has to handle, that becomes very different and easy. Additional lanes could be provided in either direction, which would allow use of a shorter cycle length. Unfortunately, in many cases signal time is considered with a fixed design already in practice, and only where right of way is available. Most urban areas you do not get land. Where is your land? So, you cannot really widen, but if you can widen, you can handle larger volume of traffic. So, only where right of way is available or a new intersection being constructed, major changes in the number of lane can be considered. Otherwise, what I have shown here, make it 3 lane, make it 2 lane, this may not be possible in reality in all the cases. That is a constant. And finally, the optimal solutions are found more easily when physical design and signalization both are treated together. So, that is one very important point. Wherever there will be an opportunity, the physical design, physical infrastructure intervention and signalization together can produce better result. Of course, always it may not be possible to have physical design changes or physical infrastructural intervention in that sense. So, altogether we discussed here about the pre-time signal design using the Webster method, discussed with you about the estimation of flow ratios, loss time, green time, calculation of cycle length, all this. Then the concept of critical lane and also the concept of time budget, how to calculate the critical lane volumes, relationship between number of pin lengths and the cycle lengths, how the whole thing can change and how you can calculate the desirable cycle length. With this, I close this lecture. Thank you so much.